To module number 14, and this is going to cover Le Chatelier's Principle. So this is pages 6, 7, and 8 in your notes for unit number 4. Le Chatelier's Principle is basically what happens to a system at equilibrium and how that system can shift. So how can you take lots of reactant and make product, or take lots of product and make reactant? And one of the biggest applications of Le Chatelier's Principle is in this process called the Haber process, which is described down below in this little video right here. And you're going to watch that one. It's a TED Ed that talks about the industrial application by making nitrogen fertilizer. Because we know we have lots of nitrogen in the air. 70% of our air is nitrogen gas, but that nitrogen isn't in a usable form. And so they figured out how to make nitrogen on a big scale. And then that nitrogen can then be used for fertilizer and make lots of food. So it's been one of the most important chemical reactions on the planet. Okay? All right, so what is Le Chatelier's Principle? Well, this is the wording you're going to use when you talk about Le Chatelier's Principle. Here's your definition right here. And it simply is about what happens to a system at equilibrium. And remember, when we're talking about a system, we've got a closed system, so nothing's going to enter or exit. So it could be a physical system, like we talked about in the last module, where I've got water going into a gaseous form back into liquid state, and that is a system. It could be a chemical system, but it has to be closed so that no reactant or product are entering or exiting. It's just what's going on inside of this system. Okay, so it says when a stress is applied to an equilibrium system, the equilibrium is going to shift to reduce the stress, and as a result, a new equilibrium is going to be established. So how do you do that? What is a stress? Well, a type of stress on an equilibrium system are any of the three down below in the note. So we're talking about the concentration of something. Okay, what happens if you increase the concentration of the reactants? The concentration of the products is going to get more. What happens if you increase the concentration of the products? You're going to make more reactant. So we're going to say, is that change of concentration shifting the equilibrium in the forward direction, or is it shifting it in the reverse direction? So we're going to talk about it in terms of what's the stress, which way does the equilibrium shift, and then what's the result that you get. Okay, so again, one stress could be changing the concentration, increase the concentration or decrease the concentration. Second stress could be adding or removing heat. It's going to be really important to recognize, is this a system that is absorbing heat? So is it an endothermic reaction, or is it a system that's releasing heat? Is it an exothermic reaction? So if you increase the heat, it's going to depend on whether that heat is on the reactant side or the product side. What's going to happen, right? And what if you decrease the heat? So these are all the concerns. These are all the complications that we're going to be looking at when we deal with some questions, which are actually kind of fun to solve. You just have to actually just think about what the stress is, and then does it go this way or that way because of what the stress is doing. Third stress, the change in the volume of a system. This is only going to affect an equilibrium that involves all gases, because you have to remember that solids and liquids aren't compressible, okay? So the equivalent is like the change in, you guessed it, pressure. Because if you decrease the volume of a system, can you see right here? What's happening? You're decreasing the volume, you are increasing the pressure, and that's the same as talking about increasing the concentration. What does that mean? It means you have more collisions and more successful collisions with the correct collision geometry. And so you're going to have more reactions taking place. Okay, so I'm going to leave you with this section right here. Now would be a good time to pause my video, watch the Haber process below, and pick it back up again at the very top of this page. Write out the thermochemical equation. Okay, back from the pause. Good. We've got our balanced thermochemical equation, and you saw in the video there that we're taking nitrogen from the air, we're reacting it with hydrogen gas, and we're producing our ammonia, right? And once we've got our ammonia gas, that's essentially what you're going to be able to use in order to make the fertilizer. So here are some concepts in this table here that we're going to look at that have to do with the shifting the equilibrium and what actually happens. So the system change. Well, the first thing that we're going to do is we're going to increase the nitrogen gas. So what's the stress on our equilibrium system? We are increasing the concentration of the N2. Our nitrogen is on the reactant side. So if you increase the concentration of the nitrogen, you now have more molecules. They're going to collide more often with the hydrogen molecules. You are causing more successful collisions. And as a result, you are shifting the equilibrium in the forward direction. Okay? Reactants to products, you're shifting it in the forward direction. And as a result, what's going to be the result? Well, you're going to increase the concentration of the NH3. Are you going to make more heat? Yep. You're also going to increase the amount of heat that's released. Okay, so can you see the key wording there? And I would highlight that. What's the change to the system, meaning the equilibrium system? What's the stress? Which way does it shift? And what's the result? Okay, and that's how you want to think of this equilibrium constant. So let's do the next one. The next one is, well, what if you inject some non-reacting gas into the container? So we're talking about, well, what if you added some noble gases to it? These aren't reacting gases at all. So are they going to cause any shifting to this equilibrium? No, no stress, because they're not part of the system at all, right? So you're going to have no shift. And you're going to end up with no change in the equilibrium. Okay, next one. Let's talk about what happens when you change the heat. Here we have to recognize that heat's on the product side because it's exothermic. Okay, there's my heat right there. If I increase the heat on the heat that's on the product side, it's going to shift it in the reverse direction. Does that make sense? Other way. If the heat was on the reactant side, it would shift it in the forward direction. But you have to recognize where the heat is for the reaction system, the equilibrium system that you're dealing with, and plan it accordingly. Okay, so if you increase the heat and the heat is on the product side, it's going to shift it in the reverse direction. So the reverse reaction, you could say towards the reactants. And notice that we're still calling the reactants because they're on the left-hand side, and the products because they're on the product side. Yes, of course, you could write the reaction in the opposite way, but that's not what we do for equilibrium systems, okay? Just keep it written as is, and we always refer to what's on the reactant side as the reactants and what's on the product side as the products, even though if you're increasing the heat, those are really the reactants, and then you're making the products, but don't confuse yourself with adding that in and doing any flipping at all. Okay, so increase the heat because it's on the exothermic side, shifts it in the reverse direction towards the reactants. What's the result? You are going to increase the concentration of the nitrogen gas, you are going to increase the concentration of the hydrogen gas, and you're going to decrease the concentration of the NH3 gas. That's the result. Okay, two more to look at, and then we're going to be done for today. What if we increase the volume of the container? Okay, here's where I've highlighted in green our coefficients, and that's why it's really important, because when we're looking at the volume and we're looking at a change in volume, it's only affecting a system that is a gas. Is this a gaseous system? Yes. Every molecule on the reactant and product side are gases. How many do we have? And this is where you do a count. Okay. In total, I have 4 molecules, or 4 moles, however you want to consider it, doesn't really matter. 4 things on the reactant side 2 on the product side. So you count up your coefficients. How many are you dealing with? Okay. If you increase the volume, you're decreasing the pressure. That's your stress. So I'm decreasing the pressure on this equilibrium system. Which way does it go? If you're decreasing the pressure, it's going to go from the low number to the high number, which means the reverse reaction is favored. It's going to go towards the reactants, and you're going to end up with all the things you had from the top. I'll fill this in nice and neatly and post it, okay? Last one. What if you add a catalyst? Does that have any effect on a system at equilibrium? What do you think? Here's your answer. No. No stress. No shift. Why? Because if you're adding a catalyst, you're decreasing the energy of activation, and that is favoring the forward direction the same amount as it's forwarding the reverse direction. And so there's no effect by adding a catalyst to a system that's at equilibrium. Remember that one, okay? That's one of the ones that can trick people up later on. All right, what I want you to do is fill in this table down below and come back to it, okay? And then I want you to work away on page number 8. These are the questions. If you memorize these shifts always as an increase, you're gonna have a little more success, okay? Don't try to memorize what happens if you decrease something. Just go for what happens with the increase, and by default, if you decrease the stress, it's gonna go the opposite way. So this table on page number 8, is my summary, okay? I'm gonna fill this in with you quick, and then I'll let you get to work. All systems, if you increase the reactant, okay? If you increase the reactant, is it gonna shift to the product or the product to the reactant? Which way is the shift gonna happen? If you increase the concentration of your reactants, you are shifting to the right. Decrease is just gonna be the opposite way. But don't memorize the decrease, just memorize all the increases, okay? Nothing if you add a catalyst. Exothermic, you have to remember that it's like saying you've got the heat on the product side. If your heat's on the product side and you are increasing the temperature, it's gonna shift it which way? To the left. It's gonna shift it towards the reactants. Good. Endothermic, you're going to be like, yep, I've got my heat on the reactant side. If I increase the heat and it's on the reactant side, it's going to shift it to the right. Okay, so I'm memorizing increase, it's going to go to the right. If I have an equal number of reactant and product molecules, and those molecules are gases, no change. I have the same number of reactants and product molecules. They're going to be affected the same way. There's no change or no shift to the equilibrium. And if you have things that are different, so let's say you've got a system where you've got 1X on this side and 2Y products on this side, okay? If you have more gaseous product than the gaseous reactants, what's going to happen? If you decrease the container volume, you are increasing the concentration, which means you're going to have more reactants happening, more successful collisions, and it's going to shift it from high to low. What do we mean? So if you're increasing it, the pressure, it's going to shift it to the left, because again, can you see right here? I have 2 to 1. It's going to shift it to the left. If you increase the volume, you're decreasing the pressure. It's going to shift it to the right. And if you add anything that's a non-reactant gas, you get no shift. Okay, so think about this. This again is your summary table. Try the questions down below, and then we'll check your solutions And good luck with that. This is probably the trickiest lesson so far.